Now the Navier-Stokes equation consists of the pressure, the gravity, and the viscous forces, right, equivalent to the mass times acceleration. Now before you arrive at this equation, you need to make several assumptions. That is, the fluid you're working on should be a Newtonian fluid. That is, the viscous stress should be proportionate to the rate of strain or rate of deformation. The fluid is to be incompressible in isothermal, constant density and temperature. Now the Navier-Stokes equation can be used for problems in 2D and 3-dimensional space with the following formulas over here, right? And the derivation, of course, will allow us to arrive at these equations. Now the Navier-Stokes equation is essentially derived from the Newton's second law of motion, force equals to mass times acceleration, the forces being body force, surface force, and the body force is represented by the gravitational force mg, surface forces being represented by pressure and viscous forces. Now when we derive the Navier-Stokes, we are essentially assuming an infinitesimal cubic cell in space immersed in fluid, and we have the pressure and the shear stresses. Sigma xx x plus dx distance away from the origin, sigma xx x at the origin. Similarly for shear stress at the top and bottom surface, and for zx at the back and the front surface of the cell. Now we are going to derive in the x component, where we have rho dx dy dz, which is the mass times g, gravity in the x direction. That is represented by the gravitational body force. Then we have the pressure force times the dy ds, dz, that is the area normal to the force, and sigma x x dy dz similarly for all other components equals to rho dx dy dz times the acceleration, mass times acceleration. Now this whole equation, of course, can be simplified into this equation by dividing by dx dy dz, and we arrive at this equation. Over here we have sigma xx x plus dx minus sigma xx x, right? So now we are going to assume that this sigma xx minus sigma xx is very small and can be cancelled off. We arrive at this equation, and by the Newton constitutive relation, we have the stress tensor that we can use to substitute into this equation and arrive at this equation. So basically we are just substituting formulas, and we arrive at this equation where we have the continuity equation that can be cancelled off. Now over here we have rho du dt, that is the mass times acceleration side of the equation. So we have converted it, expanded it to this equation, rho du dt, du dx, dx dt. Now du dt is represented by the acceleration, and u is also a function of x, y, z, and t, of course. So the chain rule has to be used in this equation, and essentially we arrive at this equation where dx dt is equals to u, dy dt equals to v, dz dt equals to w. And we arrive at this equation, rho g minus pressure gradient, viscous force, mass times acceleration.